The multi-label classification task is a practical vision task that has received much attention. However, as the number of samples and semantic concepts increases significantly, annotating all possible labels for each image is very difficult. Collecting a partially annotated multi-label dataset is an alternative and feasible strategy. Partial annotations save time and labor costs considerably. Models trained with partial annotations perform poorly due to insufficient supervision. The self-training framework is used to solve the problem. Known labels are utilized for training a model first, then the trained model is used to generate pseudo-labels for unknown labels, and at last, the model is trained by all labels again. Current ST methods focus on label correlations or instant similarities and class distribution estimation. With a low proportion of known labels, the number of positive labels is scarce, which brings challenges to the learning of ST framework. Supervised learning determines the direction of model optimization and affects the reliability of the generated pseudo-labels, further affecting unsupervised learning. The known labels of each image in the training set contain fewer positive labels and more negative labels, thus the classifier of each class excels at classifying negative samples rather than positive samples. Meanwhile, more unknown labels exacerbate the positive-negative imbalance. It is also worth thinking about how to complement unknown labels under negative dominance. This is an overall illustration of the proposed ST framework. Different data augmentations are fed into the encoder to extract feature maps, then go through classification head to obtain the corresponding possibilities for optimization. First, let's talk about the motivation of saliency regularization. If the prediction bias of a true positive sample is generated by the negative dominance, then the activation of the corresponding region in the spatial dimension is suppressed. With a low proportion of known labels, the regional overfitting of a class on some specific spatial regions occurs. To mitigate the negative dominance, reinforcing the activation of the object region corresponding to a present label is desired, thus we use heat maps to model the saliency of the object region. For convenient and meaningful optimization, CAMMC is utilized. The resulting optimization problem is J theta. To simplify the problem, we only optimize values selected by the top operator on AC, commonly, PC is computed as predicted probability. When YC is 1, AC is close to the positive infinity direction. When YC is -1, vice versa. This is also consistent with the optimization direction of J theta. So the optimization of J theta is simplified as PC hat. We also raise two propositions. Adding the saliency regularizer SC to the logit AC can also address the imbalance of easy and hard samples and focus on semi-hard samples. SR makes the saliency enhancement different between non-object and object regions from the perspective of gradient. General pseudo-labeling is as follows. When U is identity transformation, pseudo-labels are easily affected by thresholds, and high thresholds bring a lesser extent of optimization to the model. Training on self-generated labels can easily lead to overfitting. Pseudo-labeling based on CR is following label consistency of the same image. Because the network outputs of strong and weak augmentations from the same image are discriminative, the generated pseudo-labels drive further model optimization. To further recall possible positive labels, PC hat is used to generate pseudo-labels. This is an overall optimization of the model. Our method achieves state-of-the-art results on different datasets and different metrics. Meanwhile, we explore more modes and backbones, even large-scale datasets. Our method achieves very good results. Ablation study verifies the effectiveness of different modules and different hyperparameters of our method. Probability distribution is used to analyze negative dominance, hard samples and semi-hard samples. The SR-based trained model can better distinguish missing labels. These further illustrate the effectiveness of SR. Visualization is used to show the saliency improvement of object regions and results of complementing unknown labels.